Check, check. Yes, you can hear me.
Bez pointera?
Sorry?
Okay.
Do we have a clicker? No, we do not have a clicker.
Okay.
We'll just use the laptop. So, good afternoon. My name is Serge Bazanski, and I was supposed to go to the next slide. How do you work this thing? There we go. Perfect. Hi. So, my name is Serge Bazanski. I'm a wannabe hardware hacker. I mostly do DevOps work these days.
Yeah, and I'm Michał, and I do a lot of random reversing stuff, and sometimes I do some cryptography. And I think that's all.
So today we wanted to give you kind of a more a lighter talk. After seeing how to exploit Cisco ISA devices, this is something much more silly. So we just happened to have a very old Protégé laptop. It's not your fastest machine these days. And it arrived to us with this following problem. There was a password. And I do not really remember why that happened, but I really, really wanted to unlock the darn thing. There was just like an inner thing. When you own a device, you must be able to actually use it. You know, even though it's a 14-year-old laptop. So, you know, it looked like a password prompt. Let's just try clearing the CMOS by using a reset pin. But no, there's no such thing as a reset pin on this laptop. Let's try yanking out the lithium battery and see if that resets it. No, the password is still there. Let's take, this is a recommendation from the internet, let's take a bunch of keys and scrape them across a flash chip to see if there's a checksum error, and then the password disappears. No, but it's quite a nice idea. But if we kind of mess around with the laptop while it's asking for a password, if you do notably Control-Tab, Control-Enter,
yes,
you get this prompt. And when you see something like this, I immediately just think, OK, I'm just going to write a keygen. I don't care anymore. I need to keygen this thing.
It was probably meant for Toshiba at the service to unlock laptop. It wasn't meant for the end users.
Right. Afterwards, we talked to some people, and yes, this was apparently a service recovery setup. So we have a keygen. We have a key checking function that we need to analyze it. It's probably in the BIOS. What do we do?
Yeah. So it was quite obvious that the code we want to look at is in BIOS. So we wanted to start the BIOS analysis. But the problem is how to get the BIOS code. The most obvious idea for us was to just dump from physical memory. But the problem is that we had only that one locked down laptop. So that wasn't an option. We could also just desolder and dump the BIOS flash, but it's a lot of work. So I decided to look at the BIOS updates. Maybe I will be able to unpack them. So I went to support Toshiba.com. Then I found some exe file with updates. Then unpacked it with 7-zip. And I found a lot of files, which the most interesting one was this one. It started with some nicely looking header. You can see the BIOS string. You can see a version number and laptop model. So,
yep.
So it looks like a BIOS update blob. But the problem is that right after this plain text header, we had compressed data. So we knew that right, some MIG problems. Okay, so we knew that they are compressed because they were smaller than the BIOS chip, BIOS flash. So what to do now? Okay, the problem was that the format was unknown. And the default unpacker was 16-bit executable, so...
You really don't want to reverse engineer that. That is not
definitely.
a fun evening.
But after that, I found out that if I download a newer update blob, just a newer version, then we have 32-bit installer. So let's look at it. we have an executable which uses DLL, which uses TB decode DLL, which sounds promising, and it has some nice exports, especially the last one, which sounds like BIOS update decode file. So what I did was to just write 50 lines of C code, import the DLL, and just call the functions on the binary blob. And voila, I got the plaintext dump. You can see some plaintext strings probably from the setup menu.
So all without even looking at a single line of 16-bit assembly. But at the same time, while Redford was working on doing this the software way, I just figured I have a free evening, I'll just dump the flash chip. So how do you actually look for a flash chip on a laptop? This is this beautiful Toshiba that we have here. This has actually quite a bit of chips, and it's still surprisingly densely packed for such an old machine. So if you don't know, there's basically a very simple rule. If your chip is long and narrow, it's probably RAM. If it's wide and short, it's flash. Otherwise, Google it. And armed with this lead hacker knowledge, we managed to find the actual flash chip. But now what? So there's a few ways you can go about this. It depends on the flash chip, depends on how you're feeling that night. In my case, I just wanted the contents of the flash, and I just really went for desoldering the chip, connecting it to a clip or breakout board, and dumping it that way. If the chip actually supported JTAG or some other serial protocol that you can use in circuit to program or read the thing, I would have probably used that. It might have even had to use that, but again, I was fixated on just desoldering the thing. And again, since this was a quick effort, I just ripped up a board in KiCad. I did the typical home setup, thermal transfer, and sodium persulfate etching. And I use a hotter gun and a cheapo soldering iron to kind of move the chip over. If you want to replicate that sort of extreme hardware hacking, you'll need a soldering iron, you'll need a hotter gun, and you'll just need a stable hand. If that is the cost that it's kind of hard to stomach, I highly recommend just joining a hackerspace. It's probably cheaper than owning the tools, and you get good company, and you end up just being on New Year's Eve and etching PCBs in a pot because your proper tank broke. It's fun. So this was my finishing setup. I think it was 4 years ago, 5 years ago, I managed to recover this photo. And yeah, you can see this is the flash chip, which lives now on a gorgeous breakout board connected to an old Spartan FPGA dev board that I had lying around with just a bunch of cables. And if you're crying internally, shouting, why the long cables, why? This is going to cause you pain. You're right, it will cause me pain later. This is another shot. And this more or less the setup I used. I just had a state machine running on the dev board that was queried via UART from a PC, give me this block. It would do the actual parallel talking via a protocol called AAMUX, which is like muxed address and data from it's actually an Intel standard for firmware hub chips. And I got back the actual data. It wasn't so easy. Of course, I had issues. I forgot checksums. Who need checksums? That was fun to debug. I also mixed up the address lines. That was fun to debug. So lessons learned, don't use an FPGA even if you really, really, really want to, unless it's absolutely necessary. And please simulate your designs before you just start connecting cables together. We should have used the microcontroller seriously. But yeah, now we know. So yeah, I ended up with the same dump as Redford, and we could now start actually analyzing the code. Just try again.
Okay, yeah, it works. So now we had a correct BIOS code dump. So what to do next? I was totally new to BIOS analysis, so I had a lot of very trivial questions. For example, what's the CPU mode right after the reset? Also, what's the entry point? And probably the most important question, what's the memory map? So, because we just had a big binary blob, which is mapped somewhere in the memory. So we started with Intel manuals.
Volume 3, the best volume.
Yeah.
No, seriously, it's the best volume.
It says that right after the reset, the processor enters real address mode, and right after this sentence, there is a very nice table which shows you the initial values for all registers. So, for example, the interesting part of this table is in yellow. We want to look at the EIP and CS to calculate the entry point address. Yeah. So that's the calculation. We had to take EIP and just add CS base. And this way we got a linear address. And after that, we know it's real mode, so it's also a physical address. But and 820 is enabled, so we don't have to care about bit flipping. So what's there? We know the physical address, but we have no idea where it points. So I started with reading Northbridge manual to see if it mentions anything about this address, and there was nothing there. So maybe let's look at the Southbridge manual. It was another Intel chip, and it has something like that. The range right at the end of the 32-bit space was annotated as FWH, which means firmware hub.
Which is the chip we found earlier.
Yeah. So, and the good part was that the size of the range exactly matched the chip size. So it was a right direction, probably. And also, there were a lot of different mappings, all of them enabled by default. For example, you can see that right at the beginning of the memory, in the E part, there's also a copy of the BIOS flash. And the second to the last, you can see FFE. This is the original address with the 820 line disabled.
So if your CPU just happens to boot in without 820 enabled, it will still work?
Yeah, it's probably if reset happens during the 820 disabled mode. Yeah. Okay, so let's look at the entry point, because now we know where to map the BIOS blob. We had just a jump. You can see that it switched the shadow part of the segment register. And now we are in the different mapping of the BIOS. And another jump. And we see some code which looks like CPU initialization, like disabling interrupts, enabling 820, just in case. And
so yeah, now we knew it was a legit dump, and we could actually spend a few glorious hours, or glorious tens of hours with IDA Pro.
Yeah. So let's look at on the higher level, on the initialization code. So there was no stack at all, and also no RAM, because the processor just started. So you don't have any writable memory. And as far as I know, the BIOS didn't use the cache as RAM trick. So the code was very tricky. So it uses 16-bit protected mode and also Unreal mode from time to time. 16-bit protected mode is protected mode where segments are 16-bit, and Unreal mode is just real mode with shadow part of registers changed. So there were also a lot of checksums, just in case. And finally, RAM initialization and self-copy into RAM, just probably for speed up. So the protected mode means segments. And segments means like more complicated memory mappings, which were definitely used by the BIOS. So we had to find the GDT and decode the mappings, because there were a lot of for jumps and calls in the code. And we had to do that to analyze the code because really, most of the code was jumping between segments. And after we did that, you can see reading the code wasn't that hard. For example, you can see the password or challenge response prompt. It checks a flag and either display a password prompt or challenge response. Yeah, it seems easy. Like I got all the code, just have to read it and find the response checking code. But everything, like if I looked at the password checking function or challenge response code, like everything landed up in a very complicated function with like 100 sub-functions. And the higher level API looked like it takes a buffer with data and returns another buffer. So it looked suspicious. And after a long reverse engineering, I found out that all the bytes are just sent to two I/O ports, 62 and 66. So what's there?
Microcontroller.
Yeah.
What? What microcontroller? So it turns out if you find a service manual for this laptop that there is indeed a microcontroller. It's a Renesas M16C class chip, which, looking at the naming, started off as a keyboard controller and now is an embedded controller in that laptop. And it just happens to hang off the LPC bus, so it can just respond to requests on I/O ports.
Yeah, so the first what I thought was I will download the updates like exactly the same way I did with the BIOS. Just download them, unpack, and I will have the code. But there were no updates. So that's kind of a problem. Also, I tried looking at the BIOS update log, because the EC updates are quite often shipped alongside the BIOS updates, but nothing there. Finally, I found a different laptop model, which was very similar to ours, and had one EC update available.
On the website. So, nice.
Yeah. So let's look at the update. It starts similar, and this is the different part. We have a Windows driver, which is quite big for a driver. It had 300 kilobytes. So I reversed it and found 3 update blobs with 3 different firmware versions. So the installer used the same ports, 62 and 66, to send the updates. So it started with the small part, which like 2 kilobytes, and then sent the rest of the update blob. So you can see a clear problem here. Like we knew that the update blobs look obfuscated.
Or encrypted or compressed or whatever.
Yeah. And we don't have the compression code. Like it's done on the EC chip. So it's like more like self-update. So maybe try some analysis of the blobs. Maybe it's like poor encryption or some popular compression. So I looked at the entropy, and it was very high. So it was either encryption or compression. Also, I did some statistical tests, and there were nothing interesting there. So it's probably encryption. Also, all the sizes were divisible by 8. So this strongly suggests some block cipher with block size 8. And there were no long repeating substrings. So if it's encryption, it's definitely not ECB chaining mode. So nothing interesting we could decode there.
So after maybe 3 years of being kindly asked by Redford,
Yeah.
can you please dump the code of the EC? I finally sat down and did it. So what is the EC? The EC in this case was a Renesas M16C chip, as we said before. This is a symbol from a datasheet of the closest thing we could find that actually had public documentation. The pins matched and the marking on the chip was extremely similar. We're kind of skimming over what architecture it is. It is, of course, some weird Japanese obscure architecture, because why not? And there's no disassemblers for it. That's a story for another time. I made another breakout board for it. I just brought out all the pins for power. I made sure they're all tappable so I can do some power analysis. And I also brought up pins required for a programming mode. So how do we actually dump this thing? Well, the programming mode I'm talking about, they call it serial I/O. It basically, the chip contains a boot ROM. If you assert some pins, if you strap some pins at start, it will go into the boot ROM, and then the boot ROM you can talk to it over a simple serial protocol from a programmer. It's kind of like SPI. It's clocked by the programmer, both the transmit and receive data, but it also has a busy line, which means the microcontroller is telling you, no, I will not process this now because I'm busy doing something else. This is an example of a trace of this protocol. You see, you send it, the lines are labeled the wrong way. The RxD is what's sent to the chip. So if you send the chip a command asking for version, it then just replies in ASCII saying, hey, I'm version 0.1.01. Nice. So you'd imagine you can just send it a request saying, hey, bootrom, give me this page. And the bootrom is like, yeah, sure, here's the page. But no, there is a readout protection, thankfully, or thankfully not. And the readout protection means you can program it an ID code. And if this ID code is programmed, you have to pass it before any sort of flash request is handled by the bootrom. Interestingly, the ID code is actually kept in the highest bytes of the interrupt vector table, because that's a perfect place to store crypto data.
Yeah, so this gives you a way to just lock down the chip after programming.
And of course they did. Nice. That's proper security, right? So yeah, we're supposed to send the thing an ID check, they call it, if it's a command. And then we can ask it for status, and the chip says, hey, I am unlocked, and then you can actually do send requests for flash pages. So yeah, now there's an ID code that we have to get, and it's locked, so we can do all the fun stuff like side channel analysis and fault injection, have a nice picture for Twitter, but maybe not so fast. As I said, the chip basically doesn't respond at all if you send it an ID code that's either correct or incorrect. It just sits there, and when you request status, you get the result. So if you're thinking of doing timing attacks there, not really. There's nothing really to time off. However, there's this peculiar busy line. And maybe they did something stupid, right? Maybe the timing is odd. Let's run some tests. If we just measure the time between the last pin we sent, the last digit of the pin we sent, in this case the last falling edge of our own clock, and then the busy line being disasserted after the chip verifies the pin and internally checks whether it's correct or not, and then we graph that, there's an outlier. Apparently, if you ask it with the byte code, with the pin starting with byte FF, you get a 3 microsecond longer response. That's not good. So you can just pull off a classical timing attack. You enumerate the key, for every byte of the key, you just send one of the bytes, see if it takes longer to respond. If that takes longer to respond, that's the first byte of your key. So yeah, with just 0x100 times 7 checks, you can just get the key, and it pretty just falls out. And you get strings, yay.
Yeah. And then it's worth noting that the bug was in Renesas bootloader. It wasn't a Toshiba bug.
In the boot ROM, actually. So yeah, good luck patching that. This is the setup I used. This time, again, I used an FPGA, though I knew what I was doing, kind of. And it clocks the chip, and it sends commands and types the results. If you want the code, it's there. It doesn't handle all the M16C class chips yet, but there's other vulnerabilities in them. Watch this space.
Yeah, so finally I got the dump from Serge and started looking at the code. So you can see that the first half of the dump, it had like 100 kilobytes or something like that. It contained like 700 functions, some data, a separate crypto section, probably because of updates. They didn't want to they wanted to separate the crypto code to a different flash segment and a bootloader. So the good part of the problem was that the code was much simpler. Like, I had only 700 functions, so it's even possible to read all of them. So this seemed simple. There were no strings, so it may be hard to find interesting parts, but we know what to look for. We know that which was the protocol between BIOS and the EC. So there's probably some call table with, which handles different comments from BIOS. So it was quite easy to find the table. And once I got the table, I enumerated, like, I found 100 calls. So it's really a lot. I didn't expect so many calls. And we knew the interesting numbers because I reverse engineered the BIOS code. So I knew what number is responsible, for example, for password checking. So it sounds easy, but there were some tricks ahead of
Because of course, just shipping Japanese architecture microcontroller with weird instruction set is not enough. You also have to obfuscate it by running your own RTOS, or something like an RTOS with manual context switching.
They had very strange context switching. They used some mem copy on the stack frames, like from some point on, to switch the threads. So this was quite a good obfuscation. Also, there was no call convention. All the functions were just taking random inputs in random registers. And the worst of this was that, like, half of the functions were like splitting all the results to the globals. So it was very painful to read and to reverse. Also, they had a lot of, like the code was probably manually crafted in assembly. Like the whole handler's code was just some random assembly blocks connected with jumps and also some jumps to the middle of other functions. So a lot of mess. But let's look at some calls. For example, password check. On the BIOS side, it was just calculating an MD5 hash of the input, trimming to the first 8 bytes, and appending the enum for password type. So it like user password or master password. And it was sent to EC. And the response was just if it's OK or not. So at the EC side, I looked at the handler, and it was quite complicated. And 6 levels down the call hierarchy, I found this thing. It's I/O on pins 40 and 41.
Just not again, please.
Yeah.
Not again. But
yeah, for me it seemed like another security chip.
But if you just looked at it, it was an EEPROM that stored the actual data of the password.
Yeah.
Oof.
Yeah, I was pretty scared at the moment. So it just contained the hashes of passwords, and that's all. So let's look at the challenge response, because we are not interested in the password. We want to break the challenge response and to be able to create a keygen for this. Yeah. So how the challenge response look like? On the BIOS side, it's very easy. It's similar to the password. They calculate MD5 of the serial of the laptop, trim to the first 8 bytes, and prepend some randomness from RDTSC. And it is sent to EC, and the result is just converted to ASCII and displayed to the user. But on the EC side, it was a bit more complicated. The randomness from the RDTSC was mixed into the global entropy pool. Then they extracted 7 bytes from the pool, calculated a simple checksum, appended, and this was the second part of the challenge. And they also mixed the result with a PC serial. And that was the first half of the challenge bytes. And the response. So after user entered the response text, the BIOS converted that to 16 bytes and just sent the bytes to EC with a different call number. And the result was like 0, 1, if it's OK or not. So this is the EC side of the response checking. The pink blocks are derived from the challenge. So when the EC is asked to generate a challenge, it saves that pink blocks, like that MD5 of the serial. And now it uses this to verify the response. So it does some scrambling. You can see that DEC and ENC functions. It checks the second half of the response with a simple checksum, also scrambles the result, and it XORs that 3 parts and compared to the first half of the response.
And
so
they have to be equal. So we basically have to craft the first part to match the second part, knowing all of this.
Yeah, so it's quite, if you know all the code, it's quite easy to break this. Because you know everything, and you just have to set the first part of the response to make the XOR equal 0. So what is that ENC and DEC? This is a custom 64-bit block cipher. So no surprise. But it's not too interesting for us, because we know all the code, and the keys are inside the dump. So what I did was to just rewrite the code in Python, and demo time.
Hopefully.
Yeah.
Can we have the camera? That is not the camera.
Yeah.
Oh, it's off. There's a problem. Any help here, please?
Okay.
It is on.
Okay.
Help is coming.
It is on.
Yeah, it is on. Oh, it's bent.
Nope.
Nope. Yes.
Can you hold it like this?
Mm-hmm. If it works, sure. Yeah.
Oh, almost.
Oh.
Oh.
Yes, perfect.
Okay, let's boot the laptop. And
There we go.
yeah, you see the password prompt.
Control tab, Control Enter.
Yeah, challenge response. So let's rotate the camera, or maybe move the laptop. Yeah.
The 0 serial is, I think, I might have hit the EEPROM a bit too hard at some point. Exciting. Yeah, correct.
Yeah.
Yep. Yep, there. Focus. Focus. No? Yeah, you can kind of see.
Let's compare.
Yeah, close enough. Yes, that's it. We have a few more slides for you. So, there. That's nice, but you know, we can unlock a laptop. That's all fun and games, but that's not it. We also want to decrypt the updates just for completion. And turns out we just can. It just works. It's the same crypto, it's the same keys, and you know, it's symmetric signatures. Symmetric what?
That was interesting. We found symmetric signatures. So once we knew the keys, we could just generate our own signatures for just any updates.
Right, so we can basically craft our own AC code and, you know, add some bonuses to it. So, nice. How's it like on newer laptops? Well, if it's in broke.fix it. We checked, you know, we started with a 14-year-old laptop. It turns out that they not only didn't change the code, they didn't change the keys in the newest Toshiba laptops. So now, we started with a 14-year-old laptop that I just wanted to unlock because I don't know why. We can unlock any business laptop. We can craft and plant permanent rootkits in the EC, and then we can do some other fun stuff.
Yeah, so if you have some business Toshiba laptops, you can try pressing Control-Tab, Control-Enter on the BIOS password prompt.
Should be the same thing. Oh, they did change the architecture. It's not the Renesas anymore.
Yes.
They went through like 2 other architectures, including Arc, I think.
Yeah.
Same code.
Like
same code.
For the EC, they changed like the microcontrollers twice, but
Same
still
keys.
kept the old code.
Rootkit in EC. Well, there's a few obvious things we could do about it. Some of the embedded controllers, unfortunately not ours, can just be a DMA master on the LPC bus, so they can just DMA system RAM. If not that, you can still do some fun stuff like keylogging. This EC, of course, has a permanent storage attached to it, so you can keep your keylogs. And then you can do the classic, you know, key injection. This is basically also the keyboard controller. You can both sniff and emulate the keyboard from the EC.
For example, you can sniff the hard drive password at the boot and like reply it with some magic combination.
Yeah, so basically, nice. And since both the BIOS code and the EC code weren't great, we're fairly sure you can just look a bit at the BIOS, send it some funny packets, and it's going to explode from the EC.
Yeah, they had 100 calls, so...
There must be a bug.
Yeah.
Since we found this quite hot, we actually did contact Toshiba. This is the response we got. They say that they are working on a fix. It should be out any day, but it's getting slightly delayed apparently because of some current other mitigations for Spectre and Meltdown. Okay. Questions?
Questions? If I can't see you, you can yell.
Did you check if the BIOS is protected from the operating system? So, I mean, what privileges do you need in the operating system to push the AC or the BIOS update?
You need to be ring 0 unless you find more bugs.
It's pushed through the I/O ports, so you need to be in ring 0.
And are the BIOS and EC updates files signed or downloaded over HTTPS, or can you man in the middle and hijack the updates on the fly?
Oh, we didn't look at the update mechanism for I'm fairly sure just supposed to download them from their site, and I think it is over HTTPS.
For that old models, you were supposed to just download the executable and run it.
Okay.
But I have no idea how it is now.
Thanks. Cool talk.
Any other questions? Looks like that's a no. Thanks, guys.